Hello, everyone. My name is Semih, and just like Peter said, I'm doing my PhD at Imperial College with Peter Vincent. And although Freddie is located in Texas, he is my PhD co-advisor. My talk today will be about introducing a local line coupling in the context of high-order flux reconstruction schemes. I would like to emphasize differences between explicit and implicit solvers in the beginning. First of all, with explicit solvers, there is a maximum time step limitation, which could be quite limiting, especially with high Reynolds number flows. On the other hand, with implicit solvers, memory requirement is high, and these algorithms are not perfectly suited to modern hardware. And on top of this, we know that, especially with wall-bounded flows, the coupling is maximal in wall-normal direction. So my proposition is that if I introduce an implicit-like coupling near wall region only in the wall-normal direction, I could get a performance benefit. I could increase the time stepping, I can relax this constraint. This line implicit idea is not a new thing, actually, especially in the context of finite volume literature. This was explored in detail, especially with round solvers, for example. Near wall region, you have a stretched element, and this small distance from wall increases the stiffness and puts a pressure on the DT constraint. So you cannot increase your DT freely, and you are limited. This becomes a serious problem with high Reynolds number flows. So what people do with this line implicit idea is that they just couple some points along a wall normal direction, and they solve these points implicitly while keeping the rest of the domain explicit. And there have been a good performance improvements by utilizing this method. In this picture on the left, you see a 3-element airfoil where lines are formed near wall region, combining those small distanced solution points to each other. And on the right, there's a picture, so this is applicable in 3D as well. And you can also extend this line coupling in the break region if you have stretched elements over there as well. There's also an example in the context of BG. I would like to start with the figure on the right, which is a nodal BG. So here you see the red point, the one we are interested in, is coupled with all the solution points in the cell. And although it is not quite visible from this picture, there are overlapping points from the neighboring cells on the face. So there's also a contribution from neighboring cell, which increases the coupling and number of non-zero entries in the matrix. So the middle picture is a bit better in this sense, because the coupling is only along some lines, but there's still coupling from the neighboring elements. And in this case, it is not only one solution point from the neighboring element, because you are interested in the phase value, and that phase value has to be extrapolated using all those 4 blue points. But there's still an improvement in terms of number of non-zero entries. But the best in this sense is the figure on the left, which is line BG. There is still overlapping points from the neighboring elements, but the coupling is restricted along lines, and the number of non-zero entries are reduced even further. So what I'm going to do on top of this is that I'm going to limit the implicit coupling only in one direction within an element. So there won't be 2 lines, but there will be only a single line, which is aligned with the wall normal direction. And I will also ignore all the couplings from the neighboring elements so that I can get a simpler and element local matrix. This will be much easier to implement than fully implicit methods and will give me a benefit in terms of time saving. So this is a generic implicit formulation. I didn't introduce any simplifications here. So the bold J letter indicates the Jacobian matrix. As I just described, I'm going to remove all the couplings that comes from neighboring elements and from all directions but the polynomial direction. So by this way, I will achieve a local matrix, and this will make the implementation easy, and there won't be a huge memory requirement. Here in this picture, you see the non-zero structure of the element local matrix I get. This is for the earlier equation for a quadrilateral element with p equals 2. There are mainly three terms contributing to this local element matrix. One is the x derivative term, the other is the y derivative, and there is also time derivative term. And my aim here is to remove all the contribution from the y derivative. So I am going to remove all the contributions that comes from this blue plus sign. But I have to be careful about the diagonal line because both x, y derivatives and the time derivative term overlap with each other. So I have to be careful and remove only the y-related contribution from that. So in terms of construction of the Jacobian matrix, there are three different methods. The first one is the analytical formulation. It is indeed possible, but complicated. The other way of choosing the Jacobian matrix is by doing some numerical differentiation. This is more expensive, but easier to implement. So in the beginning, I decided to go with this approach. In this approach, you just perturb a field variable with epsilon, and then call the right-hand side equation, and you get the divergence of flux. And then you simply do numerical differentiation to get a column of your Jacobian matrix. And if two field variables do not lay in their stencil, you can actually perturb these values simultaneously in order to reduce the total number of right-hand side calls you need to construct a Jacobian matrix. To do this, you need a coloring algorithm, and at the end, number of right-hand side calls you need to construct the matrix is a function of number of colors, number of field variables, and the polynomial order, and the dimension, of course, which would be 2D or 3D. Before moving on to more practical examples, I would like to show a very simple example as a proof of concept. So my proposition is that this one-directional coupling removes the CFL restriction in that particular direction. In order to show this, I developed a 2D test code where I can set the polynomial order in x direction and y direction independent from each other. So in this picture, you see a mesh. The junction points of lines indicate solution points. We are not seeing the individual elements here. And the polynomial order is set to 2 in x and is set to 4 in y direction. I'm going to change the polynomial order in x and monitor how the CFL constraint changes. Here I just used a dark scheme as a time integrator, and I didn't enable the local line implicit here. I just changed polynomial order in x and y, and as you can see, it is symmetric. And as you increase polynomial order, you're getting a constraint restriction. But when you enable the local line implicit, in this table, the local line coupling is introduced in x direction. So by keeping py constant, when you increase polynomial order in x, there is no additional restriction is coming to the system. So my proposition in the beginning is simply correct. Now I will move on to more practical examples. So this is a 2D cylinders to a toy problem, Reynolds number 200. I'm not going to give detailed comparison in terms of accuracy because there is no difference in accuracy. There is no price that we are paying in terms of accuracy because we're enabling local line implicit, and it is not getting any better either. It is the same. My baseline result here is BDF2 with power to the second. And when I enable line coupling in this exact time integrator, I am getting a 9x speedup. However, this is a compressible solver, so the easiest I could get a solution is by utilizing a standard Runge-Kutta scheme. So I did this as well. I used a standard Runge-Kutta 4-5 scheme. With PI controller, where the controller aims to use the biggest allowable time step. And with respect to the baseline result, there is 3x speedup. So if you compare the local line coupling with the best available speed, there is still a 3x speedup. The next test case is ST7003 link at Reynolds number 40,000. And this picture shows the Q criteria. In the beginning, there is a linear separation, and then there's transition turbulence. Again, I'm not going to do a comparison in accuracy. I'll just do a performance comparison. The same UDF2 with earlier series coupling is the baseline. And when I turn line coupling on, this is I have around 3x speedup. But again, this is a compressible solver. So with standard RK45 with PI controller, I'm getting a 2.6 speedup. So if you compare the line coupling versus the best available, in this case it is only 1.1. But the work is still ongoing in this study. Brian actually just gave a good summary of p-multiplet and adaptive time studying features we have in PyPark. Next thing I'm going to do is enabling p-multiplet with my local line studying formulation so that we can add the gains up and get a better performance. This is the end of my presentation. Thank you very much for listening. If you have any questions, I'm more than happy to answer.